Okay, hello everyone, and welcome for all people here in the room and people connected in Zoom for attending this new colloquium from the Severo Ochoa program of the IAA in Granada, in Spain. So it's our pleasure today to have with us Dr. Elena Fomenko, or Fomenko, if we will say that the Spanish way. And so Elena made a PhD in physics and maths in the main astronomical observatory in Kiev, in Ukraine, in 2004, and currently she is a research scientist at the Instituto de Astrofísica de Canarias in Spain. So she has been mostly working in solar physics, magnetohydrodynamics wave theory, theory of partially ionized plasmas, quite some magnetic fields, and spectropolarimetry. One of her research lines is the study of the interaction of solar waves and magnetic structures. The main milestone of this line is the creation of a numerical code called Mancha 3D, a non-linear code that solves the equations of non-ideal magnetohydrodynamics in 3 spatial dimensions, including realistic ingredients. Her current interests focus on the investigation of the influence of partial ionization of the solar plasma onto the processes of energy propagation and release. And for this, she got funding from both an European Research Council starting grant in 2011 and a consolidated grant in 2017. And today she will be talking to us about multi-fluid solar chromosphere. So Elena, thank you very much for accepting the invitation to give this talk. And the floor is yours.
Thank you for this presentation, and thank you to those who came. I understand that probably solar topic is far from somebody's here. So let me start introducing the topic. So I will be presenting today the latest results of what we have been doing in our group, as I see, in the last almost 10 years, maybe 8 years. And the topic of this, as you see, is multi-fluid solar chromosphere. So what we do is we study solar chromosphere, but we do it differently from the standard approach that has been there in the field. So we try to go beyond a standard magnetohydrodynamic approach, okay? So I will explain later what it means. And for those of you who don't know what the chromosphere is, but of course everybody knows, chromosphere is called chromosphere because, of course, during the eclipses, we observe this beautiful image. We can see these prominences, these features, clouds here, that you can see them actually in this red color because you have H alpha emitting there in the red. And that's why it's called chromosphere. So it's a very narrow layer, about 1,500 kilometers in the atmosphere of the sun, which is below the bottommost level, the photosphere and the corona. And this layer is interesting because sometimes it's called like purgatory of solar physics, because it's kind of a layer which you cannot study using many approximations because everything is kind of out of equilibrium. So you don't have radiation in equilibrium, you don't have the plasma parameters in equilibrium. You cannot approximate that something is strongly magnetic or strongly plasma dominated, etc. So everything is more or less the same order of magnitude in the chromosphere, and that's why it's so difficult to study it theoretically. And of course, we know that chromosphere is a region where our solar eruptions originate, and from there they drive magnetic field lines in the corona, and then we have flares, we have coronal mass ejections, and space weather, etc., etc. Then there are a couple of big questions regarding the chromospheric physics. So one of these questions is this fantastic dynamics that we see in this layer. So what you see in this movie, for example, it's quite an old movie that has been taken at the Swedish Solar Telescope in La Palma Island. And we see here changes through the H alpha spectral length file. So when it comes to the continuum of H alpha, you see the granulation structure, which is the photospheric level. And then when it goes higher up through the line profile, you start seeing the fibrils. And fibrils are the chromosphere. So these things are one on the top of the other. So you see chromosphere has completely different structuring. And these tiny fibrils, they also follow magnetic fields, and they have they're also very highly dynamic. And then, of course, on the top of that, there is a big question of chromospheric or also coronal filling. Because also we know from observations of spectral lines in the chromosphere, because we see them in emission, we know that the temperature on average behaves like this black line. So we have a rise of the temperature in the chromosphere. But if this atmosphere was in the thermodynamical and radiative equilibrium, we should have something like a green line here. And this difference is, it needs to be explained somehow. So we know that this cannot be supplied by the radiative energy. So this needs to be supplied by some mechanical energy or some magnetic energy. So the question here is how to explain this chromospheric rise. And then finally, why do we have transition region in the hot corona? So there are like big questions about the chromosphere, about the heating mechanisms, and about the structure and dynamics. And this is what we globally try to answer in our project. So if we talk about, let's talk about starting conditions. So what do we have there? So we have here, for example, it's an example of a recent modeling that a postdoc of my group has been doing, Ana Maria Navarro, which shows how beautiful loops expanding in corona. So this is an image that shows part of the subsurface layers of the sun, photosphere, chromosphere, and then corona. So we have solar atmosphere, which is extremely strongly stratified medium. So from a point of view of a plasma physicist, when everybody wants to study plasmas which are unbounded, homogeneous, everything is nice and easy to resolve, this is not the case here because we have a very strong gravitational stratification. So your density here in this vertical direction, it changes by orders of magnitude. So it's all very, very stratified, and also in the horizontal direction, it's all very inhomogeneous. But then we also have a photosphere, which is a region which is marked here, about 500 kilometers, where we have a gas, because it's not a plasma, we have a gas, which is strongly collisionally coupled, but it's very, very weakly ionized. It's only 1 or about 10,000 particles, or even less, which is actually an ion there. So it's almost neutral gas. And this fact, it has been known for a long time from the point of view of radiative transfer, because you know that this is neutral hydrogen there. But from the point of view of plasma physics, somehow people prefer to close their eyes and prefer to think that this is still a plasma. So it's kind of contradictory, right? Because you have something which is almost neutral, but you have it very, very strongly collisionally coupled. So even this single ion that is somewhere there, it also produces a strong effect because we see it in observations. But we need to take this into account. And then in the chromosphere, which is like here, we still have half neutral plasma. So we have half neutrals and half charges. But then, since we go to the chromospheres higher up, we have density which is much lower. And in this situation, our collisional coupling becomes weaker. So we have these two populations of charges and neutrals that are not fully collisionally coupled. So just imagine the like blue balls and red balls, and then they move separately together. So if we had like a situation when everything is fully collisionally coupled, so everything should move like a single stream. But because of this lack of collisional coupling, because of the very low densities, these populations, they can move differentially with respect to each other. And this is what produced this multi-fluid effects in the chromosphere. But then on the top of that, of course, we have corona, which is again fully ionized, but then it's almost collisionless. So it's a very interesting system from the theoretical point of view. And in order to understand it, it's important to break big questions into the smaller questions, because always when you want to answer some big question, you don't know from where to start. It's very frequent. So the problem seems too big to you to start from. So it's important to break these big questions into smaller questions, and then smaller questions into tasks. And then these tasks you can do little by little, and finally probably you can have your problem solved. So if we break these big questions into small ones, we can ask, for example, the following. So how is it possible that we have magnetic conductivity between the subphotosphere, interior of the sun, and corona through this layer of almost neutral plasma in between? So how is this magnetic field lines, how do they continue through this layer? And what are the effects caused by neutrons? And then the next question, okay, maybe we need to care about that, but is it technically possible and feasible to model ion-neutral interactions in realistic solar conditions? So is it possible to create the models like the one we see here, but fully taking into account the presence of neutrals? And the last question is, do we need to care about this at all? I mean, do we have any observational confirmations of these ion-neutral effects? or maybe there are some hints or whatever. So what do the observations actually tell us about this? And if I lose you on my way of talking here, I start to directly jump to the conclusions. Okay, so there are some take-home messages. Okay, here. So yes, I will try to convince you in the rest of my talk that neutrals are very important because they can efficiently convert magnetic energy into the thermal energy, and here's the chromosphere. Then in the stratified atmosphere, like the one of the sun, the ion neutral effects, they manifest themselves at rather low frequencies. So this is not like plasma frequencies where you have to go to very high frequencies. In the stratified atmosphere, you can see these effects actually at frequencies of the order of millihertz. Then, yes, we can model ion neutral interactions in realistic situations, either in single or multi-fluid, but we need a hell of a numerical resolution to do that. So our current numerical volumes, they don't resolve it fully. And then it's very important, these multi-fluid effects are especially prominent at the borders of cool coronal features, like coronal rain and coronal prominences. And then, yes, observations, they may start showing hints for this uncoupled behavior of ions and neutrons. Okay, so these were my conclusions. But let's hear the full story before. Okay, so I will be talking about models of waves, magnetoconvection, cool coronal features, and some observations here. So let's start from something very simple. Let's transport some energy by means of waves. So we have solar waves of a typical frequency of the order of a millihertz, which are periods between 3 and 5 minutes. This has been known. And we also have been told that multi-fluid effects, they start to be important when your charge neutral collisional frequency is of the order of the wave frequency. And this conclusion came from the modeling in unbounded and homogeneous plasma. It's logical because when your wave, even particles, they start to collide with each other, then of course, if your wave frequency is similar to the collisional frequency, your wave cannot propagate, and of course you break your wave, and then this effect becomes important. But then, if this is like that, so one doesn't have to worry about multi-fluid effects still very high frequencies of the order of hertz. So let's see, in the sun, here are the typical collisional frequencies. So this is the collisional frequency in seconds -1, and this is the height in the photosphere and the chromosphere. Okay, so we have to care about two values: the charges neutral collisional frequency and neutral charges collisional frequency, because it's not the same to collide one neutral with many charges or one charge with many neutrals, right? So it's a different thing. So the important quantity here is neutral charges collisional frequency, because it's how our neutrals transmit momentum to the charges. And this is of the order of 10 to the 2 seconds -1. Our wave frequency is 3 orders of magnitude below here. So it's much, much, much lower. But still, let's try to make a simple experiment and just try to propagate a magnetoacoustic wave through the chromosphere. And have a situation which is like that. So we have a gravity pointing downwards. We have a horizontal magnetic field, which is also supported by observations. And we have a wave propagating transverse to this magnetic field. So this will be fast magnetoacoustic wave. So if we do so, we can obtain something like in this picture, where we have these waveforms as a function of height in the chromosphere. So we have them for 3 wave periods, one of 1 second, 3 seconds, and 5 seconds. Okay, these are not 5-minute oscillations, but these are seconds. This is really high frequency, but at least these are not hertz. Okay, so this frequency we can, is a good instrumentation, we can try to attempt to measure already. Like 5-10 second waves, we can already measure in the sun. So you see what happens to these waves. They start propagating in a stratified atmosphere, and their amplitude increases with height because of the density decreasing. So we want to conserve kinetic energy. So our velocity increases in response to the density decrease. But then after some height, you see that this wave, instead of increasing, it goes away. So it's kind of a decrease of the wave amplitude, and then after some height, for some periods, these waves disappearing. So this is what ion neutral collisions are doing. Okay, so if, for example, but again, I mean, at no place we cross the height where this wave frequency is actually equal to the collisional frequency. So this happens at frequencies which are significantly higher than the collisional frequencies, and this is because you see the situation where your wave frequency is equal to collisional frequency, then this wave is dumped in one period, okay, and then it's gone. Here you see a situation that it needs many periods of this wave to actually go away, but since this wave is very high frequency, so it eventually will go away, okay, and it will not reach even the height where it should be dumped through this effect. The curious thing from here is that as we go to higher periods, to lower frequencies, the curves, these red and green curves that you see here, they start to separate. And it means that our charges and our neutrals, they start behaving separately. So oscillation in charges and neutrals, it's a different oscillation now. And that happens in the volume where plasma beta is smaller than 1, so if a magnetically dominated situation. So the conclusion from this is actually gravity and this charge neutral damping. These are two competing effects. And what they do is actually producing these high frequency waves to be linearly damped before they show in any significant ion neutral decoupling. But for the low frequency waves, they actually can reach higher. They will be still damped, but then we will show this decoupling. Okay? And then you may want to ask me, so why do I at least care about this decoupling? So I care about this decoupling because if we decouple velocity of charges and neutrals, then we have a friction between these components, and we have a frictional heating. And as a result of this frictional heating, we will have an increase of plasma temperature at the places where this frictional heating is the maximum. So according to the same study here, if we compute the temperature increase as a function of height, and also different curves are different times for all these three waves, we see that first they produce temperature increase at different places in the chromosphere. So the short period waves, they increase the temperature at the bottom, but then longer period waves, they propagate higher. And if you continue in this direction, so we will hit like higher and higher layers, that means of these waves. And also since these guys here, they have been able to increase the amplitude more than other ones, they also hit more, okay? So this is a kind of a counterintuitive result here, because we have been told that the most important waves for these effects are actually high frequency waves. And what we see is the contrary. We see that actually lower frequency waves, they reach higher, they can decouple, and they can hit more and in higher layers, okay? And this is because we taken into account the stratification. So we conclude that yes, ion neutral heat friction is a good candidate for heating the solar chromosphere in any of these multi-fluid or single fluid descriptions. You need strong magnetic field to decouple charges and neutrals. So this would only happen where you have small plasma beta. So you have to have your magnetic forces important enough to decouple your neutrals from your charges. And then also this result, which is counterintuitive. So our low frequency waves, they actually hit more and at higher heights. Okay. So this was just a simple example. Now, if we go to the sun, we know that the whole sun is magnetic. So if we go to the very quiet magnetically quiet region of the sun, like this one shown here, which is a famous map by Hinode, that was analyzed, I don't know how many studies it has been analyzed, in many studies. So this is one of the most studied maps of the quiet sun, I think, in the history of solar physics, probably. You may see that this is boring, but of course it's not, because if you look at this in polarization, you see that this is full of magnetic fields. So this is full of this salt and pepper pattern, which reflects the action of what we believe now is a small-scale solar dynamo. Okay, so these are very, let's say, rather weak magnetic field compared to sunspots, but still they concentrate itself in these bigger patches which correspond to network, and then internetwork, and then interiors of this internetwork. So magnetic field is everywhere. But also we know that this magnetic field is located in the region where we have a lot of neutrals. So we want to ask ourselves a question: what are the consequences of this quiet sun magnetic field for the heating of the solar chromosphere? So now we have a mechanism that we can dissipate this magnetic field. So can we really heat the chromosphere by means of this quiet sun magnetic field? So for that, we have been doing lots of simulations of realistic magnetoconvection recently and published several papers. And our strategy lately has been performing very short time series of these simulations, where we produce data like the one shown here, which is a piece of the sun here in the photosphere. And then we do these simulations in several magnetic field configurations. So we do small-scale dynamo, but we also compare with some kind of unipolar initially vertical magnetic field, which more resembles maybe network regions. And also we do this in 3 different resolutions. We do this at 20, 10, and 5 kilometer resolutions in order to see the convergence of these multi-fluid effects. And we do this by adding or removing different ingredients. So we either have simulations where we call clean, so we just have a poor MHD situation, or we have simulations where we add, for example, ambipolar diffusion, which is equivalent of ion neutral friction. Okay? So I will be comparing this. And then we run short time series to be able to compare the snapshots one-to-one. So, for example, this compares the models with different resolutions. This snapshot gives us the vertical velocity field at the height of the middle chromosphere at 2 different resolutions, at 20 kilometers and at 5 kilometer resolution. So you may see that if you have done this at 5 kilometer resolution, you don't want to do this at 20 anymore because it looks much better. So you have all these shock fronts well resolved, you have all this turbulence and vorticity and everything much better resolved. And the dynamics of these layers is really, really interesting. So on the left, again, I'm showing the vertical velocity. And on the right, I'm showing the vertical component of the magnetic field at the corresponding height in the chromosphere. So you see that the chromosphere is made of shocks. So you don't see the granulation pattern anymore at this height. What you see is this collision of different shock waves producing vortices. And the corresponding magnetic field is also very violent. So you see this also black and white salt and pepper pattern here. But of course, at this resolution of the numerical data, you see it much better than in the observations. So you see it very clearly, like magnetic sheets and everything that is found here. So this situation is much more difficult to analyze than these simple waves that I have shown to you before. Okay, so this is really difficult to disentangle different physical mechanisms that are taking place here. Because you have waves, you have convection, you have vortex flows, you have shocks, and all this plays a relevant role. And if you change the magnetic field, then it starts looking completely different. This is another model where instead of this small-scale dynamo, what we did is to implant it initially a vertical magnetic field of 50 Gauss, and then we let it evolve. And then eventually in the chromospheric height, you have something like that. So your flow in the chromosphere, the one on the left, it has a completely different pattern. So you have all these kind of flower-like structures, and these are different types of waves that we have there. These are not acoustic shocks, but these are fast magnetic acoustic waves, essentially. And also in magnetic fields, you have a completely different structure. You don't have this black and white salt and pepper pattern, but you have patches of a homogeneous unipolar field and this field free incursions that you have there. And I don't think they have been observed, but maybe they can be observed as well. So these are different models, okay? And then we want to compare them, and we want to see if we, by adding ambipolar diffusion into these models, we are able to hit the chromosphere. So for that, we first analyze these models and we check if, for example, they have similar properties as the magnetic field and floating flux, etc. So, for example, this shows how the average magnetic field changes with height in all these 3 models. In the black curves, these are the runs for the small-scale dynamo. And in blue and red, these are unipolar runs with different magnetic fields here. So you can see, for example, that for the small-scale dynamo, the magnetic field is going to 0 in the upper layers, it's going to very small values. And this is because this field is typically very big, so you have these small magnetic loops that close very low in the photosphere, okay? But for the unipolar runs, the magnetic field continues quite high to the upper part of the domain, and then we form this magnetic flux. So they're quite different. You also may see that at slightly change in the resolution, the magnetic field becomes higher when you have better resolution. And this is because the small scale dynamo depends on the Reynolds numbers. And of course, when you reduce the resolution, you increase the Reynolds numbers, your dynamo becomes more vigorous. And that's why you concentrate your magnetic field more and you have stronger magnetic field here that you can check here. But the question here is, we want to study ambipolar diffusion, and we want to check if we actually resolve this ambipolar diffusion by constructing models at higher and higher resolution. So for that, there is a simple check. So we can compute a parameter called lambda A, which is a typical ambipolar diffusion scale. And this is measured as the coefficient of diffusion divided by the Alban speed. And the diffusion coefficient is proportional to the neutral number density squared, to the magnetic field squared, and it's inversely proportional to collisions. And this is the Alban speed. So we want to have our grid cell in our simulations to be of the order of this parameter, lambda A. And now we want to check how many grid points in our model actually satisfy this criterion. Okay, so this is what we do. And here I'm showing again the map of temperature in gray, and in colored pixels are the locations where we satisfy this criterion. So where we actually resolve ambipolar diffusion effect. So you may see that, for example, for models with unipolar fields, this is quite unsatisfactory because all of this is gray and there are very few points which are colored. And here in the dynamo models, there are more points which are colored, but still there are a lot of gray areas. So I was a little bit disappointed when I did this because I put a lot of effort in producing these models with very high resolution. And then I found that, I still cannot resolve the ambipolar diffusion in most of the points. If we make statistics, we get something like this figure here. So it shows how many % of the points of the volume we resolve as a function of resolution and the type of the model. And you may check here that at most, for the best case of this dynamo model at 5 kilometer resolution, we resolve maybe 15, 17% of the points. So, okay, it's not much. But anyways, this is larger than 0. So let's only select those points. And since we have snapshots where we can compare simulations with and without a certain effect, we can do that, okay? And we get something like that. So for this, I just go straight forward and I subtract temperature in the models without ambipolar diffusion and with ambipolar diffusion. This is as a function of time, and I do it, I just average at heights and at pixels where we resolve ambipolar diffusion effect. So this shows the result for the dynamo. This is 50 Gauss implanted field, and this is 200 Gauss implanted field. You may see that in all the cases, the differences, they increase in time. So ambipolar diffusion, it keeps hitting. So if you see there all the time, it will eventually hit your atmosphere, and then this difference, for example, 1,000 second is about 600 kelvins, which is not a small effect. Then important thing is that for higher resolutions, the slope of this curve is different. So progressively high resolutions, they give you progressively higher slopes, meaning that, for example, for this dynamo, 5 kilometers that I couldn't run longer because I got run on the computing time, we would have even high increase, which means that we need to go to even higher resolutions to resolve this effect further. But it's an important effect because this is a good check, because this is a realistic situation. All the agents are coming into play, and we see that we have to go to very high resolution to resolve it, but still it's potentially very, very important. And another conclusion is that from all these models that we see here, the temperature increase is more or less the same. So all over the quiet sun, we will be hitting because of this effect. So this is the take-home messages from this part. Okay. So yes, we can model this situation, but we need much higher resolution to actually get the whole volume modeled correctly. And then I try to move to another subject, which is a multi-fluid effect for the cool coronal features. So now you may have heard that it's very fancy to call about cooling a solar corona. Actually, there will be a conference next year in Leuven about coronal cooling. So they talk about coronal cooling because not because the corona is cool, but because there are a lot of cool features in corona, like coronal rain, like prominences, kind of condensations, that are produced by cooling events in this medium. Okay? That's why I also call about cool coronal features. These features are prominences, as you see here in these dashed lines here, but it's also this coronal rain, which are the blobs of cool and dense plasma that falls following the magnetic field lines along the loops back to the chromosphere. So it's a very interesting, theoretically interesting phenomena. We believe that this is because there are some condensations of this plasma because of some cooling events. And there have been studies in 1D in multiple dimensions to understand why these blobs actually fall in at this particular speed. So, for example, our colleagues from Palma de Mallorca, they have been modeling this in 1D and also using multi-fluid theory. And they found actually that the speed of these bubbles is set by the balance between the gravity, so it's not free fall, and the magnetic pressure that is pushing back. Okay, so this is slower than free fall. Okay, but then what happens if we go to 2D? Okay, if we go to 2D, and this has been modeled by David Martin and Gomez in his recent paper, we have something like that. So you have your block of plasma like this, and your vertical magnetic field is directed along this direction. So you see that this block of plasma falls along the magnetic field lines, and then there is this funny V shape that is also formed there. And this is because your density contrast along the block is different, and since the falling speed depends on the density contrast, the central part goes faster and the sides they go slower. So at the end, we form this V shape. If you do this without a magnetic field, which is the movie next here, it will be completely different because magnetic field stops Kelvin-Helmholtz instability to develop. And if there is no magnetic field, you have your block completely destroyed. So magnetic field really plays a very important role in those blobs falling. And it has been seen also that the falling speed, they are different in 2D and in 1D if we compare these simulations. But we are interested not in just this effect. We want to study what happens if we add multi-fluid into this. Okay, and this also has been done by David in his paper published last year, and he found the following, and it's very interesting. So you see these V shapes as we have seen before, but now this has been modeled in multi-fluid. So this gives us access to actually separately understand what neutrals and charges are doing in this situation. And for this, we plot these quantities, which we call drifts, which can be horizontal or vertical. Horizontal drifts are differences between neutral and charge velocities in the horizontal direction. And vertical drifts are the same, but for the vertical velocities. Okay? And these drifts are important because, as I said, when we have drifts, the square of these drifts is proportional to the frictional heating, which is equivalent to the bipolar heating. So once we have these drifts, once we decouple ions and neutrals, we have friction, and that produces a heating. And this is what we see also here in contours. So you see here that there is a heating. So you see that along the trajectory of these coronal ring bubbles, when they fall to the chromosphere, along this trajectory, in the transition region between this cold bubble and the hot corona, all the way, you have high drifts, you have both them in vertical and horizontal directions, and you have associated frictional heating. And then this frictional heating translates into the temperature increase, which is different for charges and for neutrals, but it's equivalently large and important. So in this region surrounding the drops, we have increased the temperature by a few kilokelvins, which is a lot. So if we would observe this, for example, this would result probably in a bright feature surrounding these following drops in the data. This has not been observed yet, but we have been talking to Patrick and Tolene and other colleagues to try to synthesize this and see if we can actually detect something like that. So the conclusion is that all these cool coronal features, they have a transition layer. And in this transition layer, the multi-fluid effects are extremely important because we decouple plasma parameters and then we heat. Okay? So this is really, really important. And it can be potentially observable. And then another feature like this is solar prominences, which sometimes are observed like a curtains of materials that just falls to the solar disk. And these curtains are frequently interpreted as Rayleigh-Taylor instability. So you have this Rayleigh-Taylor instability in all kinds of astrophysical plasmas. Each time that you have something heavy on the top of something light, then we have these fingers following down. So the same happens in solar prominences, and also these prominences are made of material which is half neutral and not fully coupled by collisions. So similarly, we did lots of modeling of relative or instability for different magnetic field configurations. And here there has been a series of work published by my former student Beatriz Pesco-Braileno, where we included all kind of multi-fluid physics into this. It was including viscosity, thermal conduction, non-equilibrium ionization recombination, elastic collisions, frictional heating, everything has been there. And also we did this for different magnetic field configurations. So for example, in this, you have examples of the simulations. This is the density of charges, and this is the density of neutral in one of these, where the magnetic field was just perpendicular to the board. And here, this magnetic field was not strictly perpendicular, but there is some magnetic component in the plane of the perturbation, and that's why you see this different. So actually, by looking at the simulations, we have been looking at them for so long that we gave them names, actually, because this one, for example, this was a baby in the womb, because it looks like a baby in the womb. And this one we call the alien head, because it looks like that. Yeah. So this one has been analyzed most, the baby in the womb. So if you play the movie, we see how this develops. So initially you form these little fingers, and then they merge. And probably want to stop it. Oh, anyway, let's keep going. So what we see is that these blobs of coronal plasma, it's rising up, and then the blobs of cool and partially ionized chromospheric plasma is actually going down in these fingers. And then once these things evolve, these fingers, they are brought together by the flow, and there is a forced reconnection happening there. And this is not like an ideal Harris-Schitt reconnection. This is actually a forced reconnection, where these blobs, they don't have much as a choice and just collide together. So there is the current sheet formed there, and there are plasmoids and reconnection happening in this partially ionized plasma, and it's really, really interesting. I don't have time to stop on that, but if you have time, if you're interested, just read the papers. So again, we can compute our ion neutral drifts also in this situation. And this is what you show here. Again, I am showing the horizontal drifts on the left and vertical drifts on the right. The scale you may see here, it's in kilometers per second. So our maximum amplitude of the drifts is about a kilometer per second, which is not a small quantity, because a kilometer per second is something we can easily measure on the sun. We have enough resolution. The overall speed is about 20 kilometers. So it makes that decoupling, it's about between 5 and 10% of the overall speed, which is small, but it's not so small not to be detected. Okay, so this is something that we can actually try to go there and measure. An important thing here, you see that this, let's say, higher decoupling, you can see this in colors. It follows the locations where we compress magnetic field and we have higher current densities. And it also responds to the theory because it's proportional to the current density. It should be proportional to the current density. So in all these regions surrounding these cool coronal features, you may expect that there is some decoupling. Okay? So the question is, can we actually measure this decoupling? So we have been for quite some years behind this question and trying actually to understand if we can observationally detect anything of this ion neutral drift, because, okay, this is theoretically a very interesting project, but if we don't have any observational confirmation, then of course, why do we bother, no? Doing all this. So this is one of the examples of the work that we published back in 2016. And here again, I show you the formula for the drifts, and you see that this ion neutral velocity difference is actually proportional to the current and to the magnetic field. So again, in the places where you have strong currents, you have compression of your material, and the boundaries of these coronal features is where you expect to have this. So we went to the VTT and we scanned this prominence that you see here with a slit, okay, making the scans very, very fast because we want to detect this phenomena very, very fast. It was very important. And make sure that we target an optically stained prominence plasma. So we make sure that our spectral lines, they form over the same volume of plasma. So in this campaign, we only had two spectral lines, which was the one of ionized calcium, the infrared, and the one of helium-10 And then we measured only the velocity because we want to make it very, very quick. And here's an example. So this is the time evolution of the velocity along one of those slits. The black line is a calcium line, and the red line is a helium line. So if you look at this, you see they're the same. No? They're completely the same. But if you pay a little bit more attention, so you see that calcium at peaks, where you have higher peaks, slightly goes larger. And here it goes a little bit higher and a little bit lower. So calcium is a little bit deviating from this helium. Okay. So you do not expect large drifts, but you do expect them. And especially if we now consider this velocity not as a function of time, but as a function of a spatial direction along the slit, you may see again the same thing. So the helium curve in red, it goes smoother, and the calcium curve in black, it goes a little bit higher than that. So at places where we have strong spatial and temporal gradients, these lines start to behave slightly differently. Okay, so that goes in this direction. Then there were other independent studies, for example, by Eberhard Beer, and he also published another book last year, where he also targeted an optically thin prominence plasma, but he used other spectral lines than those that we used. So he used, for example, strontium and potassium spectral lines. And then he plotted the velocities of the neutral line as a function of the velocities of the ionized line. And here is the bisector. So if all the points would be along this line, it means that the velocities are the same. But you see that there are some points that start deviating. And that happens right at the velocities which are larger. So again, we have higher velocities in both of the lines, and we have high deviations. In a way that, again, our charges, they move slightly faster than our neutrals. And then it has been more. For example, these papers that we just got a referee report today about this, and it was positive. So we did the same. Again, it was a prominence at the VTT, but now we added more spectral lines to this study. So we have another neutral line. We have H alpha, helium D3, and we have the calcium spectral line. And also we took a lot of care of eliminating optically thick plasma. So we, after considering all this prominence, we only have been able to reliably, let's say, measure these velocities at the very border of this prominence, where plasma is optically thin. But this is, again, it's very important to be at the border, because you have seen from theory that it's at the border where you have this decoupling. Okay, so we are at the border here as well. And then here's a snapshot of the differences between H alpha and helium D3, two neutral lines, and also H alpha and the calcium. So you see that there are differences also between two neutral lines. Okay, they are not the same, but the difference with the calcium line are higher. So again, in the direction that our ion is slightly faster than our neutrons. And there have been other works also by Maciek Tapior, and it also has kind of similar conclusions. So each time we are at the border of a prominence, we can measure this decoupling. And this decoupling goes in the same direction. And that has been it. So these are my conclusions. These are my true conclusions, not the fake conclusions. So definitely, we conclude that multi-fluid effects are important in the chromosphere, because they're important for waves. They produce wave damping and frictional heating in the middle chromosphere. They are very important in the interference in the borders of the cool coronal structures, also because they produce frictional heating and also ion neutral decoupling. These effects are very important in reconnection. I didn't talk about that, but it's very important because for reconnection, you can get faster reconnection rates because of formation of plasmoids and all kind of instabilities. In the current layers, because we dissipate currents through this mechanism, and this is an important agent for the chromospheric energy balance. In the magnetoconvection flows, allowing for efficient conversion of magnetic energy into the heat. But here we have to make note that our best models, they don't even resolve the whole volume of this effect, only 15% of it. And also observations, they systematically reveal that ions have slightly larger velocity than the neutrons. Okay, and there are some future prospects of these studies, because of course not everything is so perfect. So we have been comparing, for example, single fluid and multi-fluid approximations, because single fluid is something that many people start having in their codes, and this is something which is relatively simply implementable into numerical codes. And we see now that this single fluid, which is much easier, it can be relatively well used, for example, till the middle chromosphere, so you can be good with that. But then if you go higher up to the transition region and chromosphere, definitely you need the multi-fluid because everything decouples. It's very immediate. But for that, we need a much better theory of coupling between ionization and recombination and radiation in multi-fluid. This has not been done yet by nobody. We need a better treatment of viscosity conductivity because everybody is treating these coefficients using Draginsky from 1965 book. And this is not true. These coefficients are not true because they have been computed for completely collisionally coupled plasma, and we are moving now to plasmas which are not coupled by collisions. So there have been developments, like, for example, this recent 8 papers by Peter Hunana, who is also a postdoc at the SC in this regard. And of course, we need an adequate instrumentation for measure ion neutron effects. And this is the DKIST and EST, I believe. And that's it. Thank you.
Thank you, Elena, for this talk and for the question. I will invite David Orozco, who invited Elena to manage the questions. David.
Okay, thank you, Elena. Very interesting, very nice, and very exciting topic, actually. I like a lot when you say that actually the sun in the photosphere is started than a plasma. Everybody says it's plasma, but it's not. It's something different. So first, I want to ask you if someone here in the room has any question to Elena. Yes, please.
Yeah. Well, you saw at the beginning that the measured temperature of the chromosphere is really much higher than the expected temperature in terms of relative equilibrium. And then you saw how this ion neutral grid produces a heating in the chromosphere. So my question is, to what extent that do you think that is enough to close that gap between observations and expectations, or
I think it is one of the agents, maybe, like, I would dare to say, like, maybe 50% or more, but we are not yet there because we don't model them correctly, we don't resolve them. That's the point. I mean, if we were able to produce models which we fully resolve, then then we will be able to answer this question, but not yet.
Yeah. For that, what's the resolution?
I think it's below a kilometer. So now we are running like 1,000 cube simulations, and one snapshot is about 99 gigabytes. And if you want to increase this by a factor of, let's say, 5 in each direction, I mean, we can do this. I mean, technically, you can ask time and you can produce them, but it's technically analyzing this data, it's really it's a help.
That's more realistic. When you say 5 kilometers resolution, it's horizontal and vertical?
Yeah, it's more or less like
Thank you very much for the nice talk. I have another observational question, I guess. You showed this V-shaped diagram. You said this can be observed. Yeah. So 2 questions. One is, has it been observed? If not, what do you need to be observed?
Well, these are really tiny and they're faint, right? So you need high contrast, or you need better signal to noise ratio. But I believe that probably in iris, they are kind of detecting these kind of shapes.
Oh, so it's already like
I think they observe. Yeah.
Is it comparable to the models, or?
I would say that these shapes are, I don't know if they are one-to-one comparable, but I think you got something like that.
So, any more questions here in the room? And I don't know if someone in the Zoom session has a question.
Yes, you have one question. So please open your mic and do the question.
Maybe
We cannot hear it. Even in Zoom, we cannot hear it. So it's not a problem of the speaker. So maybe you can try to write the question in the chat, because we cannot hear you.
Okay, so maybe while we wait for the people in the Zoom to write down the questions, I do have kind of 175 questions, but I will just make maybe 1, 2, or 3, basically. So my first question is there any relationship between the unipolar diffusion, so ion neutrals interaction with the solar wind?
Well, solar winds, I believe it's mostly plasma. I know that people are trying now to model solar winds, including neutrals, and I have seen, I think, like a paper maybe. There's a saying that it slightly modifies the speed of the wind, a little bit. I mean, what happens in corona, because corona is almost fully ionized, but still you have some neutral and they're not coupled, so they're still doing something. So maybe it will 5–10% modifies the wind. But I'm not sure. What's the composition of the wind?
Plasma.
Plasma.
don't
No, I don't know. Yeah, it's interesting to look at.
My second question is regarding the resolution. So I think I like a lot the Boltzmann equation. It's something that I like a lot reading. It's something that I enjoy.
Thick codes and like this.
Yeah, so do we need at some point to even go down and from MST to multi-fluid and then to go to Boltzmann equation to simulate very, very small
Kind of
scales?
considering that, but the problem is chromosphere, it's particle collision of the particle particles. So it's hard to do. People trying to do this, and it's technically possible to do, but in very small ways, maybe 5 or something like that. And maybe there you can do it technically, but not for the whole thing. Well, it's a matter of technology. I think in 10 years, maybe we'll be doing it.
Thank you.
Yes.
Вопрос можно?
Yeah, okay. We can hear you.
Ой, спасибо. Замечательный доклад. Ну, я по-русски. Почему скорости нейтралов вниз больше, чем вверх, чем заряженных? Почему скорости нейтралов больше, чем скорости заряженных?
Okay, I will translate if it helps. So he's asking why the neutrals they have larger velocities than the charges in these models. So this is because we have Lorentz force acting on charges, okay, and that produces you larger force essentially. So if you have larger force, you have larger speeds. And for neutrals, you don't have this. Okay, neutrals they only feel the Lorentz force of collisions with charges. Yeah. Okay.
Спасибо.
Okay.
No more questions? So I think we can close the talk. Thank you very much, Elena, for this wonderful talk.